Hello everyone. I'll admit, it's been a long time since I've covered this topic, but I promised I would show you some examples of functions in the projective plane. So I'll take a brief moment and address a couple of key examples of interesting functions in projective geometry. I appreciate your patience. So this function, a rectangular hyperbola, which is famous among mathematicians, has very special properties in the projective plane. As described in a book by Ash and Gross, we can trace through the points on this function in a very interesting way. Let's say we started at the point, let's say 1, 1, or really, on the projective plane, it would be, I suppose, 1 to 1 to 1. But really, I just wanted to choose any arbitrary point in the first quadrant of this function. So we'll just say 1 to 1 to 1, which really corresponds to just considering this function in the kind of regular, quote-unquote, regular Euclidean plane. It's just 1, 1. And let's suppose that we were to move to the right and trace through the points on this function, meaning we're kind of going from here and traveling, quote-unquote, in this kind of direction to the right. And so we keep going, there are more points on this function in this fashion. And so we keep going all the way to infinity on the x-axis. Now, as I alluded to earlier, there are points at infinity on the projective plane. So, and this is one of them. In fact, here is the particular point designated by 1 to 0 to 0. And by the way, this point, and this is a somewhat remarkable fact, this point happens to be the same point on kind of the other side, meaning at the far left, at least from our perspective. It also happens to lie right here in relation to our drawing. And so that's the same point, actually, what I say, 1 to 0 to 0. And so, this is what I was referring to earlier, that the projective plane serves as a covering map for the sphere, and so it really is isomorphic to the sphere. So in that sense, it wraps around, and if it goes infinitely far on one, then it's on the other kind of side of the sphere, you could think of it, and it's basically where positive infinity is the same, meaning the same point, to negative infinity. In these models, we can continue traveling rightward in this fashion from this point at infinity, but by this time we're actually in the third quadrant. That's, the remarkable fact, where we can actually wrap around the Euclidean plane, and it's really quite just amazing. It's, it might surprise you at first, but it's a legitimate thing. And so, as, I should really get to the point here. The point is you can continue traveling to the right, and you're in the third quadrant, so, maybe we have more points here, infinitely many other points, lying on this function, or, satisfying this, this equation, and so we're going to keep going to the right. We're actually getting to what you can think of as the southern pole, which is, of course, another point at infinity, as you may be able to guess. So if we consider going infinitely far, I guess, downward on the y-axis, it's designated by 0 to 1 to 0. So we're actually almost finished at this point. I'm sure you can imagine that this, in the y-axis, that line also wraps around in the projective plane. So we actually have that same point at infinity being 0 to 1 to 0 up here. And so if we trace downward, get to that point, then we're also up here, and we're still on the function, so we can keep, in theory, traversing or tracing these points on the function to the right, and we end up back here in the first quadrant, where we keep tracing points, and really we're back where we started. So what we've demonstrated is that really the homogenized function, the function, and I'm gonna write it down, xy equals z. This function in projective geometry is actually a continuous function. And that's what makes it so remarkable. If we homogenize it, we get these very fascinating properties, really. In other words, we couldn't say the same thing for the function y equals 1 over x in Euclidean geometry. We definitely could not. I mean, you can see it on screen. It's clear that the limit as the function approaches 0 of this, this function in the conventional context doesn't even exist, because it goes to positive infinity at one end, or one side, and the other side, from the right, it tends toward negative infinity. So, within that framework, the limit doesn't even exist, let alone is the function continuous. So it wouldn't meet that definition of continuity. But in projective geometry, we get something, to put it simply, it's just very interesting, and it's just, people don't talk about it that much, but that doesn't make it unworthy. Well, I may already be preaching to the choir, but my point is, this is worth researching. A second topic which I wanted to show you is actually something called the circular points at infinity. What this actually means is that we're starting with a function which is really the particular function for basically a circle, which in the conventional sense is x squared plus y squared must be equal to r squared, at least in the conventional way of defining a circle algebraically. So it's basically, a circle is a set of points whose x and y values satisfy this equation for some value of r, which, is just the radius. It can be some constant. But basically, I just wanted to mention, and hopefully I don't take too much of your time with this, but for this section, I merely wanted to say that if we started with this equation, and we wanted to homogenize it, then basically the interesting thing is that we end up with basically x squared plus y squared equals r squared times, and since r squared is just a constant, and, x, y, and z are our three dimensions, three variables, really. And let's say we want to find, I'm actually going to write that, find points at infinity, or, the projective behavior, so to speak, of this function. Then basically, at the points at infinity, if we presume that there are some of them, we basically presume that z equals 0. We set it equal to 0 and see what happens. Now, in this case, we get x squared plus y squared. Just simply substituting into here, we're getting 0. And so this, at first, might look a little bit uninteresting, particularly because we actually get some positive numbers, since it's something squared, plus another thing squared equals 0, and, at first glance, the only solution set for this equation is 0, 0. The only way this could be true is if x and y are both 0. However, here's the key point. If we expand our view, expand what kind of numbers we use, we can get different solutions to this equation. For instance, what we're probably used to using, at least in typical maths classes, is basically the set of real numbers, or perhaps the set of rational numbers, or something like that. However, we can actually use the set of complex numbers, and, again, as many of you already know, complex numbers are my favorite set, my favorite field for various reasons, and you can see this video for more info on that. But basically, let's say we set x equal to some k, some rational, or if you insist, real number, if you insist on using the set of real numbers. Rational numbers are arguably a bit better defined, but let's say we had x equals k, and so we're getting x squared equals, x squared plus some y squared equals 0. So let's just, at least for now, ensure that x is some real irrational number. I guess I've already said that, but we get k squared, so this is a positive number, plus y squared, and y, bear in mind, that doesn't have to be a real or rational number. It can be expanded, where we're considering basically y is a complex number, is what I'm trying to say. Then basically y squared equals negative k squared, and basically if we, kind of solve this relatively basic equation, we can logically deduce that y could equal, basically, it's plus or minus, we're ending up with plus or minus ki. So isn't that interesting? We have complex solutions to this equation, and in fact these are called, this is a thing, this is called circular points at infinity. It's pretty appropriately named, since we're setting z equal to 0 and really trying to find as many solutions as we can within the complex numbers. But, yeah. I thought you'd like that. So we know, for a fact now, that the solutions, basically, and instead of k, I'm going to start using lambda, actually, for that matter. I'm going to say lambda to lambda I to 0. We can know for sure that this designates a point at infinity, which is on the circle. Yeah, it's using the complex projective plane, basically. So it's kind of more than two-dimensional, as you might imagine. Yeah. But really, I thought you'd enjoy that. I remember really liking it when I learned this for the first time. So, again, thanks for watching. And, I've seen in the past that, we can analyze this even further and more in depth. And basically, actually, you're actually, I just realized something, and you guys probably realized this before, where basically we can add plus or minus to each of these, I guess. There are an infinite number, therefore, of circular points. And basically those points actually, you might be able to envision in your head that they kind of form a line with slope plus or minus I, which is quite interesting. Hopefully I can add a picture or make that easy for you to see. But anyways, thank you very much for watching. There is, in fact, a large collection of topics within projective geometry, and many of the theorems, in truth, do not use many numbers, but rather use vector spaces and other abstract ideas. So for the next few episodes of this series, I plan to describe these notions.